Every picture of the universe you have ever seen is missing most of it. Not slightly. Not by some margin that better technology might close. The observable universe contains an estimated 2 trillion galaxies. That number was published in 2016, revised upward from the figure textbooks had printed for 20 years. The old count had missed 19 out of every 20 galaxies present. 1 in 20 is what we'd been working from, and that 2 trillion is still only what we can see. The actual universe, the real structure of which our observable bubble is a fraction, may be 100 times larger, or 1,000, or infinite. No instrument ever built, including the most powerful telescope in human history, can see past the boundary of what light has had time to deliver. Not because the technology is insufficient, because the law governing it is physics, not engineering. The boundary is not temporary. It is drawn by the relationship between the speed of light and the age of the cosmos. James Webb gave us the clearest view of the observable universe ever achieved. And the clearest view confirmed that we cannot see most of it, that we will never see most of it. That limit is not a gap in our knowledge waiting to be filled. It is a wall built into the structure of reality. Subscribe before we go further, get comfortable, lie back. This takes a moment to land properly. In 1924, an astronomer named Edwin Hubble pointed a telescope at a smudge in the sky called the Andromeda Nebula and measured how far away it was. The answer ended something that had stood unchallenged since the first human looked up. Andromeda was not inside the Milky Way. It was a separate galaxy entirely, a structure comparable in size and mass and complexity to the Milky Way itself, sitting roughly 2.5 million light-years from Earth. 1 light-year is the distance light covers in a year at 300,000 kilometers per second. That works out to about 9.5 trillion kilometers. Multiply that by 2.5 million, and you have the distance to our nearest large galactic neighbor. The farthest object a human being has ever physically reached. The Moon, at roughly 384,000 kilometers, sits so close by comparison that the ratio does not translate into any everyday analogy. The Moon is the gap between your feet and the floor. Andromeda is the distance to the edge of the known world. The universe was not one galaxy. It was a collection of them. How large a collection, nobody yet knew. What exactly does it mean to be 2.5 million light-years away? The light arriving from Andromeda right now left that galaxy before our species existed, before anatomically modern humans had appeared, before any monument now considered ancient was constructed, before any language now spoken was spoken, before any city on Earth existed. The light that arrives tonight from Andromeda departed when the first stone tools were being struck from rock by creatures that would eventually become us. It has been travelling ever since, crossing 2.5 million light-years of expanding space, and it arrives now. That is the nearest large galaxy. The nearest. Every other major galaxy in the observable universe is farther. Estimates of the total galaxy count accumulated slowly over the following decades. By 1990, when NASA launched the Hubble Space Telescope, astronomers placed the number somewhere between 100 and 200 billion galaxies in the observable universe. That number felt enormous. It felt like the kind of number that closes a question rather than opens one. 100 billion galaxies. The universe is large. We have roughly counted what it contains, and the count is staggering enough to satisfy any sense of scale. That number was wrong by a factor of 20. Nobody knew it yet. In 1995, Hubble did something unprecedented. It stared at a single patch of dark sky in the constellation Ursa Major for 10 consecutive days, not a patch near a bright star, not near a known galaxy cluster or nebula, a patch chosen specifically because it appeared to contain nothing. Deliberately empty sky. Several colleagues thought the observing time was being wasted. that pointing a multi-billion-dollar instrument at apparent blankness for 10 days was an unjustifiable experiment. The image that came back made their objection look historically short-sighted. The Hubble Deep Field showed approximately 3,000 galaxies in a patch of sky smaller than a tenth of the diameter of the full moon. Some were spiral, their arms sweeping outward the way the Milky Ways do. Some were elliptical, smooth and featureless, their star-forming days long past. Some were irregular, their shapes distorted by ancient gravitational encounters with neighbours that happened billions of years before the Earth formed. All of them were real. All of them contained hundreds of billions of stars each. And all of them were packed into a region of sky that the naked eye saw as containing nothing at all. Astronomers extrapolated from that result across the full sky and arrived at a number consistent with the prior estimates. Roughly 100 to 200 billion galaxies. The deep field had confirmed what earlier surveys suggested. The number settled back into the literature as settled fact. For 20 years it stayed there. Then in 2016, Christopher Consolis and his team at the University of Nottingham asked a harder question. Not how many galaxies can we detect, but how many must exist that we cannot detect at all. They built three-dimensional models of galaxy distribution across cosmic time, accounting for every population that was too faint, too small, too distant, or too severely redshifted to appear in any existing survey. They were not counting what we can see. They were calculating what must be there based on the physics of galaxy formation and the known structure of the universe. The answer was not a revision, it was a demolition. Before Webb, we had missed 19 out of every 20 galaxies in the observable universe. Read that again. Every census, every deep field image, every careful extrapolation across 20 years of observation, accounting for one galaxy in every 20 that are actually there. The other 19 were invisible, not because anything hid them, not because better filters would reveal them, but because the light they emitted had been stretched during billions of years of travel through expanding space into wavelengths that human eyes cannot see, and that existing instruments were not built to capture. The mechanism is called redshift. When light travels through space, it travels at a fixed speed, but space itself is not fixed. The universe has been expanding since the Big Bang, and as it expands, the wavelengths of light travelling through it are stretched. A sound wave from a train moving away from you drops in pitch as the train recedes because the sound waves are being pulled longer. Light in an expanding universe behaves the same way. Wavelengths that began as blue or green visible light emitted by young hot stars in distant galaxies billions of years ago arrive at our detectors shifted toward red, or, for the most ancient galaxies, shifted all the way into the infrared, a part of the electromagnetic spectrum that human eyes experience as warmth rather than colour. The most ancient galaxies in the observable universe have had their light shifted so far into the infrared that no optical telescope, regardless of how large its mirror, can collect it. The photons are arriving. They are real. They are simply arriving at frequencies that glass lenses cannot focus and that visible light sensors cannot record. For the entire history of observational astronomy until recently, these galaxies were functionally invisible, present, real, emitting, undetectable. James Webb was designed specifically to solve this problem. Its primary mirror is 6.5 meters across, composed of 18 hexagonal segments, coated with a thin layer of gold. Gold is used because it reflects infrared light more efficiently than silver or aluminium, which is why the telescope looks warm and amber in photographs rather than silvered. The mirror's light collecting area is roughly 6 times that of Hubble, but size is only part of the advantage. Webb operates behind a 5-layer sunshield the size of a tennis court, made of a material called kapton, coated to reflect the sun's energy. That shield keeps Webb's detectors at approximately minus 233 degrees Celsius. At that temperature, the telescope's own thermal radiation is suppressed enough that it does not overwhelm the ancient infrared signals arriving from the most distant galaxies in the observable universe. Maintaining those conditions in space while pointing at different targets with nanometer mirror precision, while communicating with Earth across 1.5 million kilometers of vacuum, required years of engineering work and a deployment sequence that had to proceed correctly in order, without the possibility of human intervention, or the mission would have failed. It proceeded correctly. Webb launched on Christmas Day 2021. The launch was precise enough that Webb arrived at its operational position, a gravitational balance point called L2, with more propellant remaining than required, potentially extending its mission beyond the original 10-year target. On July 12, 2022, the first science images were released. One of those images was a deep field. It showed a galaxy cluster called SMACS 0723 in the foreground. The cluster's mass bends light from more distant galaxies behind it, acting as a gravitational lens that magnifies objects that would otherwise be too faint to detect. Behind the cluster lay thousands of galaxies at distances and resolutions Hubble could not approach. Some of those galaxies sent their light toward us more than 13 billion years ago, when the universe was only a few 100 million years old. That light left its source before the Earth formed, before the Sun ignited, before the Milky Way had its current structure. It travelled for 13 billion years across an expanding universe and landed on a gold mirror in space. That is not a photograph of the past. That is the past itself, arriving. The light is real. It came. Webb's observations confirmed and extended the Constellis revision. 2 trillion galaxies, a factor of 20 beyond the figure textbooks had printed for 2 decades. And Webb began returning findings that surprised the people who built the models that were supposed to predict them. Galaxies appearing at 600 to 700 million years after the Big Bang that are too massive, too bright, and too structurally mature for their age. Systems that should not have had time to assemble that much stellar mass. In 2023, Joel Leger and his team at Pennsylvania State University identified a population of massive quiescent galaxies, galaxies that had already assembled and stopped forming new stars, at distances corresponding to the universe's first 500 million years. The standard models of galaxy formation do not accommodate that timeline. Webb says it happened anyway. The models are being revised in real time by a telescope that has been operational for under 3 years. It is worth pausing to understand what a galaxy actually is, because the word becomes abstract when encountered in numbers in the trillions and can lose its meaning. A galaxy is not a cloud of stars suspended in fixed space. It is a gravitationally bound system, a structure held together by the combined gravity of hundreds of billions of stars, plus an enormous quantity of dark matter that we cannot observe directly, but whose gravitational effect we can measure precisely. The dark matter in a typical galaxy outweighs its visible stellar population by a ratio of roughly 5 or 6 to 1. What you see in a deep field image, those points of light, those spiral arms, those elliptical hazes, represents a minority of the actual mass present. The visible portion of a galaxy is the lit surface of a much larger dark structure, and that dark structure, the dark matter halo, extends far beyond the visible edges of the stars, sometimes to distances 10 or 20 times the diameter of the visible disk. Each of the 2 trillion galaxies Webb's data implies is a system of this kind, mostly invisible, mostly dark matter, with a luminous surface visible from billions of light years away only because hundreds of billions of stars are burning within it. The 1995 Hubble Deep Field did something beyond counting galaxies. It demonstrated in a way that was visually irrefutable that the universe does not thin out toward the limits of what we can observe. It remains populated right up to the observational boundary in every direction that Hubble pointed with sufficient exposure time. Not a gradual fall-off of galaxy density towards some edge. Galaxies everywhere, at every distance, filling the observable volume as far as any instrument could detect. That uniformity carries its own implication. There is no indication that the observational boundary represents any actual boundary in the distribution of matter. The universe does not appear to end at the edge of what we can see. It appears to continue. The Consulis study's conclusion was grounded in observational data, specifically in the fact that distant surveys were consistently finding galaxies at the very edges of their sensitivity that appeared to be the bright tips of a much larger population extending below the detection threshold. The 19 in 20 figure was not a guess. It was an inference drawn from the known relationship between galaxy brightness, size, and redshift, applied to the population distributions found in the deepest available surveys. When Webb was being designed, recovering exactly these populations was one of the primary scientific justifications for the telescope's infrared capability. There is a specific quality to the light Webb collects that deserves attention. When Webb detects a galaxy at a redshift corresponding to a look-back time of 13 billion years, the light it collects was emitted when the universe was less than 1 billion years old. That light has been travelling ever since. During its crossing of the universe, entire generations of stars have formed and been destroyed. Planets have assembled around new stars, some of them developing complex chemistry. In one known case, a planet developed biology, and that biology eventually produced a civilization that built a machine to intercept that ancient light. The photon that lands on Webb's detector has witnessed the full history of the observable universe from a particular vantage point, travelling as a silent record of the conditions at its source the moment it was emitted. When astronomers analyse its spectrum, they are reading the chemical composition and motion of a galaxy that no longer exists in that form across a distance that no physical object has ever crossed. Webb has also begun to change what astronomers know about the relationship between supermassive black holes and their host galaxies. Every large galaxy we can study in sufficient detail appears to contain a supermassive black hole at its centre, with a mass ranging from millions to billions of solar masses. The mass of the central black hole correlates with the mass of the surrounding galaxy's central bulge in a way that suggests the two grew together, each influencing the other's development. Webb has detected supermassive black holes in some of the most distant galaxies it can observe, and those black holes appear to be disproportionately large relative to their host galaxies compared to the correlation observed in nearby galaxies. Distant black holes grew faster relative to their surrounding stellar populations than the standard picture allows. Again, the models need revision. And again, the revision points toward processes in the early universe that were more efficient and more extreme than existing theory captures. The numbers that come from Webb's deep fields are worth running through a comparison that brings their scale into contact with something human. If you tried to count the galaxies in the observable universe at a rate of 1 per second, it would take you 63 million years to finish. If every human being alive on Earth today counted simultaneously, each person would be responsible for approximately 250,000 galaxies. If you wanted to travel to the nearest galaxy beyond the local group at the fastest speed any spacecraft has ever achieved, the trip would take roughly 100 billion years, more than 7 times the current age of the universe. These are not rhetorical exaggerations. They are the actual numbers that come from applying the actual physics to the actual distances. The universe is not large in the way that a country is large. It is large in a way that makes every human reference point for size, including the ones that already feel enormous, into rounding errors. The 1995 and 2022 deep fields, Hubble's and Webb's, represent 2 moments in a continuous effort to look as deeply as possible into the universe and report what is there. In both cases, the essential character of the answer was the same: galaxies, everywhere, at every distance, filling the observable volume right up to the limits of detection. The specific numbers changed. The level of detail improved enormously. The wavelength coverage expanded from visible to infrared. But the fundamental result held across both observations separated by 27 years and by the most significant advance in space telescope technology in the history of astronomy. Webb confirmed Hubble's picture and extended it, and what both pictures show is a universe whose full census remains permanently beyond any instrument operating at our location in space and time. What this means is that the 2 trillion figure is not a destination. It is a floor, the confirmed lower bound of what the observable sphere contains, and the observable sphere itself is not the universe. It is not even close. To understand why it matters that the 2 trillion is a floor rather than a count, consider what happened in the interval between the Hubble Deep Field and the Conselis revision. For 20 years, the 100 to 200 billion figure was treated as the size of the universe's galaxy population. Research programs were designed around it. Popular science writing repeated it as background fact. The public formed a picture of cosmic scale based on it. Then in 2016, that picture turned out to describe only 5% of what was there. 2 decades of settled understanding, revised by a factor of 20. The lesson is not that astronomy is unreliable. The lesson is that the universe contains far more than any instrument operating in visible wavelengths could show, and that the revision, when it came as a sudden collapse of the prior estimate rather than a gradual adjustment. Webb has not produced a comparable revision of the 2 trillion figure, but it has produced findings that nobody anticipated, formations that models did not predict, galaxies that existed too early in configurations too mature for the time available. The revision of 2016 may not be the last time the picture changes substantially. The light that forms a Webb deep field image has physical properties worth understanding precisely. Each photon in that image carries information about the temperature, composition, and motion of matter at the moment it was emitted. Information encoded in the photon's wavelength and encoded further by the redshift the photon accumulated during its transit across expanding space. When Webb's spectrographs break that light into its component wavelengths, they read those encodings directly. A galaxy 13 billion light-years away reveals, in its spectrum, what elements were present in its stars, how fast the stars were moving, and whether the galaxy was forming new stars or had exhausted its supply of gas. All of this information arrived in photons that left their source before the Earth existed. The galaxy itself may look nothing like what it did then, but the record of what it was, encoded in ancient light, arrived on a mirror in space, and it can be read. The Hubble Space Telescope remained operational for over 3 decades and continued to produce important science even after Webb's launch. Webb did not replace Hubble's scientific role so much as extend it into a new wavelength regime. The 2 telescopes are complementary. Hubble sees the universe in visible and ultraviolet light. Webb sees it in infrared, and using both together allows astronomers to construct more complete pictures of distant objects than either could provide alone. Several of the most important early Webb findings involved combining Webb's infrared data with archival Hubble observations to trace the full spectral energy distributions of high redshift galaxies. The combination reveals properties that neither telescope alone could determine. The era of large space observatories is not ending with Webb. It is entering a phase in which multiple instruments with different capabilities can operate simultaneously on the same targets from complementary perspectives. There is a number that captures the practical meaning of Webb's galaxy revision in a way that the raw 2 trillion does not quite communicate. Before the 2016 revision, and before Webb, astronomers estimated that the observable universe contained roughly 100 to 200 billion galaxies. After the revision, the estimate became 2 trillion. The ratio between the old estimate and the new estimate is between 10 and 20. Now apply that ratio to the question of what might be out there. If we missed 19 out of 20 galaxies in the count, we may also have missed 19 out of 20 of everything that depends on galaxy counts, including, if life is common in the universe, 19 out of 20 of all the living worlds and potentially all the civilizations we were implicitly imagining when we thought the number was 100 billion. The revision does not change the Fermi paradox in any fundamental way, but it does change the weight of the silence. There are 20 times more places where someone could be signaling than we thought, and we still hear nothing we can confirm. The natural assumption, when told the universe contains 2 trillion galaxies, and we have only confirmed a fraction of what is out there, is that better technology will close the gap. A bigger mirror, a more sensitive detector, more time pointed at darker sky. Eventually the whole thing comes into view. That assumption is wrong in a way that matters, not wrong as a matter of degree, but wrong as a matter of category. The boundary of the observable universe is not the boundary of what current instruments can detect. It is the boundary of what any instrument, built by any civilization at any point in the future of the cosmos, will ever be capable of detecting. The limit is not technological. It is physical. And the reason it is physical comes from one fact that changes the character of everything else. The universe has an age. The universe is approximately 13.8 billion years old. It began in an event called the Big Bang, a moment when all of space, all of matter, and all of energy emerged from a state of extraordinary density and temperature and began expanding. From that moment, light has been travelling through that expanding space at a fixed speed, roughly 300,000 kilometers per second. Fast enough to circle the Earth 7 times in 1 second. Fast enough to reach the Moon from Earth in 1.3 seconds. Fast enough to cross from the Sun to Earth in about 8 minutes. Not fast enough, in 13.8 billion years, to cross a universe that has been expanding while the light travelled. In the first 380,000 years after the Big Bang, the universe was so hot and dense that it was opaque, a plasma in which light bounced endlessly between charged particles without travelling freely. When it cooled enough for electrons and protons to combine into neutral hydrogen, the plasma cleared all at once, and light streamed outward from every point in space simultaneously. That light has been travelling ever since, stretched by the expansion of the universe from visible wavelengths into microwaves. We detect it today as the cosmic microwave background radiation, a faint and nearly uniform signal arriving from every direction of the sky. It is the oldest detectable signal we can receive, the absolute limit of observation. The edge of what we can see is not a wall, it is a clock, and the clock ran out 13.8 billion years ago. The observable universe has a radius of approximately 46 billion light-years, not 13.8 billion, as the age might suggest. The difference arises because space has been expanding while the light travelled. The sources of the most ancient detectable light emitted it when they were much closer to us. Space stretched since, carrying those sources to their current positions while their light was still in transit. The observable universe is a sphere roughly 93 billion light-years in diameter, with Earth near its centre, not because we are at any special location, but because the observable universe is defined entirely by what has had time to reach us specifically. Now hold what that implies about what lies beyond the boundary. The Big Bang was not an explosion at a point in space. It was an event that occurred everywhere in space simultaneously. Every region of the universe was present at the beginning. Every region has been expanding ever since. And in the regions beyond our observational horizon, The same processes that produce the structures within our sphere have been operating for the same 13.8 billion years. Those regions are real. They contain matter organized by the same physical laws. They have their own galaxies, their own stars, their own planets, and almost certainly their own possible observers, bounded by their own causal horizons. Looking outward from their own positions at their own observable spheres, they cannot contact us. We cannot contact them, not because of any distance that technology could in principle bridge, but because the expansion of space ensures that their light has not reached us and never will. The causal boundary is not a distance problem, it is a time problem, and time does not yield to engineering. Conservative estimates based on current measurements of the universe's geometry suggest the actual universe is at least 250 times larger in radius than the observable sphere. Inflationary cosmology, which describes a period of extraordinarily rapid expansion in the universe's first tiny fraction of a second, predicts the actual universe may be exponentially larger, millions of times larger in each direction. The formal mathematics produce no confirmed upper limit. One way to feel the ratio: inflationary models predict the actual universe is at least 10 to the power of 23 times larger than the observable portion. That is a one followed by 23 zeros. If that estimate is even approximately correct, the 2 trillion galaxies of the observable universe represent less than 1 part in a trillion of the total galaxy count in the actual universe. The 2 trillion is not a large number relative to what actually exists. It is a vanishingly small one. No observation resolves this. No signal crosses the causal boundary. Not light, not gravitational waves, not neutrinos, not any particle or force described by the laws of physics. The region beyond the horizon is causally disconnected from us in a way that is permanent and absolute. Nothing that happens there affects what happens here. The boundary is drawn by physics, and it is not a boundary that any future technology can move. You're not at the center of the universe. You're inside a bubble, and the bubble has a wall, and the wall is made of time. The causal disconnection has a name: the particle horizon. Any event that occurred beyond the particle horizon could not have sent a signal to our location in the time available, because the signal would have had to travel faster than light. For every point in space, there is a sphere of the universe causally accessible to it, and every other region is permanently beyond reach. The universe is partitioned into an enormous number of causal bubbles, each accessible to observers within it, and inaccessible to everyone else. What Webb adds to this picture is not an expansion of the bubble. The observational horizon does not move with better instruments. What Webb provides is sharper resolution within the bubble, and in particular, unprecedented access to the earliest epoch of the universe's history that our observable sphere includes. When Webb detects a galaxy whose light has been travelling for 13.1 billion years, it shows us that galaxy not as it is now, but as it was when the universe was roughly 700 million years old. The galaxy has had 13.1 billion additional years to evolve, merge with neighbours, exhaust its star-forming gas, and potentially become something entirely different from what Webb images. Every observation is a record of the past. The telescope moves only backward. The temporal character of all astronomical observation is easy to underestimate when confronted with photographs as detailed as Webb produces. But it is always present. The Sun appears to us as it was 8 minutes ago. The nearest star system, Alpha Centauri, shows us its state roughly 4 years in the past. The Andromeda Galaxy shows us its state 2.5 million years ago. When Webb images galaxies at distances corresponding to light travel times of 13 billion years, it is recording events that happened before Earth existed. The telescope is a time machine that moves only in one direction and is limited by the age of the cosmos. What exists beyond the causal horizon is almost certainly not nothing. The universe continues. Galaxies, stars, planets, the same physical laws operating across the same kinds of structures. Almost certainly in some of those structures, matter has organized itself into something capable of looking outward and wondering, and those observers are as permanently inaccessible from our location as we are from theirs. Every science article that says the universe contains 2 trillion galaxies is, precisely stated, saying the observable universe contains at least 2 trillion galaxies, and the observable universe is almost certainly a small fraction of the whole. The 2 trillion is the floor, the minimum, and within that floor, the arrangement of those 2 trillion galaxies across space is its own category of disorienting fact. The cosmic microwave background radiation is worth describing precisely, because it is the most direct evidence we have for both the Big Bang and for the physical nature of the observational limit. It is not a point source or a ring, it is a sphere. We sit at the centre of a sphere of ancient light, 46 billion light-years in radius, and that sphere is the oldest thing we can detect. When instruments like the Planck satellite mapped the CMB in fine detail, they found it nearly uniform in temperature across the entire sky, with fluctuations at the level of 1 part in 100,000. Those fluctuations are the seeds of the cosmic web. Present in the early universe as quantum variations in density, they grew over billions of years of gravitational amplification into the filaments and voids and galaxy clusters that Webb photographs today. The cosmic web is a fossil of the quantum structure of the newborn universe grown to cosmic scale. The uniformity of the CMB across the full sky creates its own puzzle called the horizon problem. In a simple Big Bang model, regions of the sky separated by more than a certain angle should never have had time to exchange energy and equalize their temperatures. But the CMB is nearly identical across regions that, under that simple model, could not have communicated. The solution is inflation, the same period of rapid expansion that explains why the actual universe is so much larger than the observable sphere. During inflation, the universe expanded so rapidly that regions initially in causal contact were stretched far apart. The uniformity of the CMB is a fossil of that pre-inflationary contact, preserved across the history of the universe. There is a thought experiment that makes the causal structure of the universe concrete. Imagine a civilization exists 60 billion light-years from Earth. Their distance from us exceeds our observable radius of 46 billion light-years, so no light from their location has had time to reach us. Now imagine that civilization points its best telescope at Earth's location. Can they see us? No, for the same reason. Our light has not had time to reach them either. 2 civilizations in a universe governed by identical physics, made of identical particles, separated by a distance that ensures permanent mutual invisibility, not because of any obstacle between them, because the universe is 13.8 billion years old, and light travels at 300,000 kilometers per second, and 60 billion light-years is too far for either to have crossed in the available time. The causal horizon is not a wall, it is an arithmetic fact. Even within the observable universe, we cannot see everything that currently exists there. We can only see what has had time to send us light. A galaxy 40 billion light-years away is within the observable universe because ancient light from it has reached us. But the light we receive from it is ancient, the galaxy as it was billions of years ago. Its current state, 40 billion light-years away, is still en route. In this sense, even the observable universe is only partially visible at any given moment. We see different parts of it at different epochs, each part at a different moment in its history. The present state of distant objects is permanently inaccessible. Cosmology is an observation of the past conducted from one particular location, and it cannot cover the current moment of the universe at any significant distance. What Webb's observations of the early universe reveal is not just a catalogue of ancient galaxies. They reveal the conditions under which the universe built its current structure. The galaxies Webb detects at redshifts corresponding to look-back times of 13 billion years are the ancestors of the galaxies we see today. By studying them, astronomers can trace the history of how matter organized itself from the nearly uniform plasma of the early universe into the complex cosmic web of today. The fact that some of those ancestors are already unexpectedly large and structured at such an early time means the universe was working faster than models assumed. Whatever process assembled those early massive galaxies was more efficient than current theory captures. Finding out why is one of the primary science objectives of Webb's extended mission. There is a specific way in which the causal boundary of the observable universe differs from every other kind of limit human beings have encountered. Most limits in human experience are contingent. A wall can be demolished. A mountain can be climbed. A disease can be cured. An ocean can be crossed. Even the speed of sound, once treated as an absolute barrier, was exceeded in 1947. The limits that human ingenuity has consistently overcome are limits imposed by specific physical conditions that do not apply everywhere. The causal horizon is different in kind. It is a consequence of the most fundamental relationship in physics, the finite speed of light in a universe of finite age. No amount of cleverness, no theoretical breakthrough, no sufficiently advanced technology can circumvent that relationship. The causal horizon is, in this precise sense, the one limit that cannot be beaten. What the causal horizon reveals about the nature of the universe is something cosmologists have known for decades, but that tends not to penetrate popular discussions. The universe is not a unified system that can, in principle, be fully observed from any vantage point. It is partitioned into mutually inaccessible regions, each with its own observable sphere and its own causal history. The full universe is not something any observer anywhere can ever see completely. Every observer at every location sees only their own slice, and the slices, while they share the same physical laws and presumably similar large-scale structures, are permanently separated by boundaries that no signal can cross. This has a specific implication for the question of whether the universe is knowable. Within the observable sphere, everything that emits a detectable signal can, in principle, be detected and characterized. Webb is a step toward that complete characterization within our sphere. But outside the sphere, the universe is permanently and absolutely unknowable from our location. Not unknowable because we lack the instruments. Unknowable because the information cannot travel to us under any physical law that operates. The universe is knowable only up to a horizon. And the horizon is not a temporary obstacle. It is a permanent feature of the cosmos. Consider the temporal character of what Webb observes specifically. When Webb detects a galaxy at a redshift of 8, a redshift corresponding to a look-back time of roughly 13.1 billion years, it is detecting light that left that galaxy when the universe was approximately 700 million years old. That galaxy is now, by our best models of galaxy evolution, something very different from what it was. It has had 13.1 billion additional years to merge with neighbours, exhaust its gas, build new stellar generations, lose its spiral structure, and potentially become an enormous elliptical system sitting at the centre of a galaxy cluster. What Webb sees is the young version, what it became in its present state. We will not know for 13.1 billion years if we or our descendants are still here to observe it. Cosmology is archaeology. Every image is a fossil. The universe as it currently exists in its present state at all significant distances is permanently hidden behind the speed of light. There is a practical consequence to the particle horizon that rarely gets discussed explicitly. The observable universe contains roughly 2 trillion galaxies, but those 2 trillion galaxies are not all being observed at the same moment in their histories. Nearby galaxies appear to us as they were millions of years ago. Distant galaxies appear to us as they were billions of years ago. The observable universe is not a snapshot of the universe at one moment in time. It is a composite of different eras, each galaxy shown at a different point in its development, corresponding to the light travel time from its position to Earth. The 2 trillion galaxies are not 2 trillion contemporaries. They are 2 trillion specimens from a range of epochs, each showing us the universe at a different age in its history. Webb, by pushing the detection boundary to earlier and earlier epochs, is extending that composite picture toward the very beginning of the observable universe's story. What exists beyond the causal horizon is almost certainly not nothing. The universe continues, galaxies, stars, planets, the same physical laws operating across the same kinds of structures. Almost certainly in some of those structures, matter has organized itself into something capable of looking outward and wondering. And those observers are as permanently inaccessible from our location as we are from theirs. The symmetry is exact. Whatever we cannot know about them, they cannot know about us. Whatever sense of isolation we might feel looking outward at a universe too large to navigate, they feel in identical measure looking outward from their own positions. The causal horizon does not isolate us in particular. It isolates every observer in the universe equally and permanently. The universe is not full of galaxies. It is full of nothing, interrupted occasionally by galaxies. The large-scale structure of the observable universe is called the cosmic web. It is not a uniform scatter of matter across a sphere. It is a 3-dimensional network of filaments, walls, and nodes, dense where gravity has pulled matter together over billions of years, with vast, largely empty regions called voids occupying most of the remaining volume. Galaxies do not scatter evenly through the web. They cluster along its threads and concentrate at its intersections. Between those threads and intersections, almost nothing at all. Start with a basketball. If you shrink the sun to the size of a basketball and place it somewhere in a city, the nearest star system, Alpha Centauri, would be represented by another basketball sitting approximately 4,300 kilometers away. The distance from London to somewhere in the middle of Asia. Between those 2 basketballs, nothing. No gas, no dust, no checkpoint, no waypoint of any kind that registers on any scale a human being has ever navigated. The scale that feels crowded in a diagram is, physically, almost entirely empty space between 2 basketballs separated by thousands of kilometers. The Milky Way contains between 100 and 400 billion stars arranged in a disk roughly 100,000 light-years across. The nearest large galaxy, Andromeda, sits 2.5 million light-years away. The local group, the Milky Way, Andromeda, the Triangulum Galaxy, and roughly 50 smaller companions, occupies a region about 10 million light-years across. The Virgo supercluster, the larger gravitationally associated structure containing the local group, spans approximately 110 million light-years in diameter. In 2014, a team led by Brent Tully at the University of Hawaii mapped a supercluster of superclusters they named Laniakea, from the Hawaiian for immeasurable heaven. Laniakea spans roughly 520 million light-years across and contains approximately 100,000 individual galaxies. The Milky Way sits near its outer edge, one galaxy among 100,000, orbiting within the slow gravitational field of an enormous structure that is itself one of many comparable structures distributed across the observable universe. Now look at the spaces between structures like Laniakea. The Bootes void is a sphere of space approximately 330 million light-years in diameter, That is larger than Laniakea, a region of space bigger than the supercluster that contains the Milky Way, and it contains almost no galaxies. Roughly 60 confirmed. Statistical models predict a region of that size should contain thousands of galaxy groups and clusters. Instead, 60. The void might as well, for practical purposes, contain nothing. Robert Kirshner and his team discovered the Bootes void in 1981 during a galaxy redshift survey. They were mapping galaxy distances across a large region of sky. In most directions, galaxies were present throughout the survey volume at the expected density. In the direction of Bootes, they found a gap, a spherical region where the galaxy distribution simply was not present. Kirshner initially questioned whether the survey had produced an error. It had not. The void was real. Further surveys over the following decades confirmed and refined its extent. Light crossing the Bootes void from one edge to the other takes 330 million years. In 330 million years on Earth, complex life went from primitive fish and shallow seas to the full diversity of the age of dinosaurs. The continents drifted by thousands of kilometers. Multiple mass extinction events occurred. Entire lineages of animals rose to dominate the planet and were destroyed. The surface of the Earth became unrecognizable from what it had been. And all of that happened while one photon was still crossing one void. Not the universe. Not the observable sphere. One void. The Bootes void is not exceptional in kind, only in scale. The cosmic web contains thousands of mapped voids, some smaller, many comparable, and voids occupy roughly 80% of the observable universe's total volume. 80%. The filaments, walls, and nodes where galaxies concentrate account for the remaining 20. And within that 20%, individual galaxies are separated from their nearest neighbours by millions of light-years of intergalactic space. Think carefully about what that means for the 2 trillion. Each of those 2 trillion galaxies is a point on a web whose dominant feature is not the threads, but the space between them. If you took the observable universe and compressed it to the size of a football stadium, the cosmic web's filaments would be threads barely visible to the naked eye. The galaxies on those threads would be microscopic dots. The voids between the filaments would account for 80% of the stadium's volume. 2 trillion galaxies sounds like a full universe. The structure that contains them is one of the emptiest things in nature. James Webb has added direct observational detail to this structure. Because it operates in infrared, Webb can detect the faint diffuse emissions from the intergalactic medium. The gas stretched along the cosmic web's filaments between the galaxies on those filaments. Observations published in 2022 and 2023 confirm the presence of this gas with unprecedented clarity. The filaments are not empty. They contain hydrogen and helium stretched across hundreds of millions of light-years in structures so tenuous that a single cubic meter of filament space contains, on average, fewer than a dozen atoms. The air in the room around you right now contains approximately 25 billion molecules per cubic meter. A cubic meter of the densest confirmed intergalactic filament contains fewer than a dozen atoms total. The ratio between those 2 densities is roughly 10 to the power of 27. There is no everyday analogy that communicates a ratio that large. The difference between the density of air and the density of cosmic filament space is not like the difference between a lake and a glass of water. It is not like the difference between an ocean and a bathtub. It is a difference so extreme that ordinary concepts of density stop being useful at the scale of the cosmic web. The filaments are the dense parts. The voids between them are emptier still. What Webb also revealed is that the filaments are not passive. They are circulation systems. Gas flows along them toward the dense nodes where galaxies cluster. Stars form from that gas. Stars die and return enriched material to the intergalactic medium. The cycle operates on timescales of billions of years across distances of hundreds of millions of light-years. The cosmic web is not a static structure waiting to be photographed. It is an active, evolving system through which matter moves at speeds and scales that make any human conception of movement look like stillness. The dark matter component of the web is invisible by definition, but its presence is inferred from the gravitational behavior of visible matter. Dark matter, filaments, formed first in cosmic history, providing the gravitational scaffolding on which visible gas and galaxies subsequently accumulated. When Webb detects a filament of intergalactic gas between galaxy clusters, it is tracing the surface of a dark matter structure whose total mass far exceeds the visible material above it. The universe's true skeleton is dark. The visible cosmic web is a luminous outline drawn over a darker underlying architecture. The matter in your body, the atoms in your cells, your bones, the air in your lungs, represents a local concentration of matter so anomalously dense compared to the cosmic average that the word unusual does not capture it. You are not a normal configuration of matter in a universe full of matter. You are a temporary anomaly in a universe defined by absence. The universe produces configurations like yours at rare intervals and at specific locations within a web whose dominant character is emptiness, and that emptiness is not static. The contrast between the Virgo cluster and the Bootes void captures the full range of the cosmic web's character. The Virgo cluster, the dense gravitational centre of the supercluster that contains the Milky Way, spans roughly 15 million light-years and contains between 1,300 and 2,000 confirmed member galaxies, ranging from dwarf systems of a few million stars to enormous elliptical galaxies containing several trillion stars each. The supermassive black hole at the centre of M87, one of the Virgo cluster's largest members, has a mass approximately 6.5 billion times that of the Sun. It was the first black hole to have its shadow imaged directly by the Event Horizon Telescope in 2019. That is what a node of the cosmic web looks like at close range. Thousands of galaxies organised around a gravitational centre, threaded with the jets and winds of supermassive black holes at the cores of the largest members. Now contrast that with the Bootes void. 330 million light-years across, 60 galaxies. That is the full range of the web structure, from its richest nodes to its deepest absences. The 80% figure for void volume is not a rough estimate. It is derived from large-scale galaxy surveys that map the three-dimensional distribution of galaxies across billions of light-years. The Sloan Digital Sky Survey, which catalogued the positions of hundreds of millions of galaxies across a large fraction of the observable sky, provided the data that confirmed the dominance of void structure at the larger scales. When cosmologists divide the observable universe into cells and classify each by local galaxy density, voids consistently account for roughly 80% of the total volume. The result appears across different survey datasets and different classification methods. The void dominance of the cosmic web is one of the most robustly confirmed structural facts in modern cosmology. Webb has also contributed to understanding how a galaxy's position within the cosmic web shapes its character. Galaxies in dense cluster nodes tend to be elliptical, red, and quiescent. Their star-forming days are past, their stellar populations aging. Galaxies in less dense filaments tend to be spiral, blue, and active, still drawing gas from the intergalactic medium and building new stellar generations. Galaxies in the most isolated environments, though sitting in or near voids, tend to be small, blue, and forming stars at a relatively high rate for their mass. The web is not just a structure. It is a sorting mechanism, organising the universe's matter into different types of objects depending on where within the web those objects happen to reside. The cosmic web that Webb photographs is not static. The filaments are slowly growing denser as galaxies fall toward gravitational high points. The voids are slowly growing emptier as matter drains out of them into the surrounding structures. The direction of evolution is toward a more extreme version of what already exists. Denser filaments, deeper voids, more pronounced large-scale structure. This would continue indefinitely, except that dark energy is working against it. The acceleration of cosmic expansion is stretching the space between structures faster than gravity can pull them together at the larger scales. At large enough separations, the expansion wins. The cosmic web will eventually be frozen, its large-scale connections severed as the expansion carries different regions of the web past the point where gravity can still link them. There is a philosophical dimension to the void structure that is difficult to ignore once you sit with the numbers. The voids are not empty in an absolute sense. They contain sparse gas, dark matter in low concentrations, the occasional isolated galaxy, and the background radiation that fills all of space. But they are empty in the sense that matters for any civilization. There is nothing to interact with across those hundreds of millions of light years. No resources within practical reach. No neighbours within communicating distance on any timescale. A civilization might survive. If a civilization were placed at the centre of a void comparable to the Buddha's void, it would look outward in every direction and see a wall of distant galaxy clusters, hundreds of millions of light-years away, with nothing between. The isolation would be absolute by any standard of what isolation means to any social creature. The universe contains these regions in enormous quantity. They occupy 80% of the observable sphere's volume. The web is defined more by its absences than by anything present within it. The cosmic web's formation is not random. It is the direct consequence of quantum fluctuations in the very early universe, tiny variations in density that the inflationary period stretched to cosmic scales. Regions that were slightly denser than average at the moment of the Big Bang attracted more matter through gravity over time, growing denser as the universe aged. Regions that were slightly less dense than average lost matter to their surroundings and grew emptier. The pattern was set in the universe's first fraction of a second by events at the quantum scale, and has been amplifying over 13.8 billion years ever since. The voids we observe today, including the Buddha's void, are the grown-up descendants of regions that were slightly less dense than average at the universe's birth. The cosmic web is a fossil of the quantum structure of the newborn universe, grown to cosmic scale. 2 trillion galaxies in the observable universe, each suspended in a web whose dominant feature is absence, 80% void by volume. And that void is not stable. It is changing in a direction that makes the current view of the universe more specific, more fleeting, and more tied to this particular moment in cosmic history than any earlier generation of astronomers had reason to understand. Walk the basketball model farther than most scale demonstrations take it. If the Sun is a basketball, and the nearest star is another basketball 4,300 kilometers away, where would the Milky Way's central black hole be? At the same scale, the Milky Way itself would be roughly 9 billion kilometers across, larger than the actual solar system. The central supermassive black hole, Sagittarius A star, would be represented by an object roughly the size of a small city. Between it and the nearest star basketball, 4,300 kilometers of nothing. Between that star and the next, another 4,300 kilometers of nothing, multiplied across 400 billion stars. The Milky Way at basketball scale is an enormous sphere of almost complete emptiness, with tiny points of light so widely spaced that the dominant experience of travelling through it would be the absence of anything to see. Now scale up from the galaxy to the cosmic web. Laniakea at basketball scale would span roughly 47 billion kilometers in every direction, 5 times the distance to Neptune from the Sun. Within that enormous volume, 100,000 galaxies, each itself mostly empty. Between the nearest 2 of those galaxies, millions of light-years of intergalactic space, The cosmic web's filaments at this scale would be threads of material spaced so far apart that crossing from one to another would require crossing distances large enough that the model itself breaks down as an aid to intuition. The intergalactic medium that Webb detects in the filaments occupies a strange position in the universe's matter budget. It contains significant quantities of ordinary matter, hydrogen and helium gas, but spread so thin across such enormous volumes that it does not form galaxies or stars on its own. It sits in the filaments as raw material that has not yet been claimed by gravity. Some of it is falling toward galaxy clusters. Some of it is being pushed outward by the radiation and winds of massive stars and active galactic nuclei. Webb's infrared sensitivity has allowed astronomers to trace these flows in ways that earlier instruments could not, painting a picture of the cosmic web as a dynamic system through which matter circulates continuously rather than sitting inert between the structures that contain galaxies. The scale of the cosmic web's voids has a consequence for the question of contact between civilizations that is independent of the Fermi paradox in the usual sense. Even if civilizations exist throughout the observable universe, their distribution must follow the distribution of galaxies, which means their distribution must follow the filaments of the cosmic web. A civilization in a filament on one side of a void like the Bootes void is separated from a civilization on the other side not just by 330 million light-years of space, but by 330 million light-years of space that contains almost nothing. There is no intermediate location to relay a signal, no way station, no stepping stone. The void is not a route to be navigated. It is an absence to be crossed in one long attenuated step, and the step takes 330 million years at the speed of light in each direction. The 2022 and 2023 Webb observations of intergalactic gas confirmed something that had been predicted by cosmological simulations, but not directly observed at the sensitivity Webb achieved. The gas in the filaments is not uniformly distributed. It is slightly denser near galaxy clusters, where the gravitational pull of the cluster has concentrated material. It is slightly less dense in the middle regions of filaments, far from any major gravitational attractor. This gradient, from the relative density of a filament's galaxy-adjacent regions to the near emptiness of its central stretches, is itself a feature of the Webb's dynamic character. The filament is not a static tube of gas. It is a flow, directed by gravity toward the nodes, carrying material that was once more uniformly distributed through the universe's earliest epochs. Consider what the cosmic web means for the question of where life could exist. Life, as far as we know, requires stars and planets. Stars and planets require galaxies. Galaxies require the filaments and nodes of the cosmic web. The voids, 80% of the observable universe's volume, almost certainly contain no life, not because the conditions are hostile to it, but because the conditions for stars to form are not present there. Life, if it exists beyond Earth, is confined to the remaining 20% of the cosmic volume, the filaments, the walls, the nodes, and the galaxies that cluster along them. And within that 20%, life must further be confined to the vicinity of stars stable enough to permit the development of complexity, orbited by planets with the right conditions. The universe is enormous. The fraction of it where life is possible is a small fraction of a small fraction. If this kind of thinking makes the universe feel more real rather than more distant, take a moment. Subscribe. Share this with someone who has never thought about what fills the space between galaxies, because what comes next is where the scale stops being about structure and starts being about what it means to be here at this particular moment, able to look at any of it. Picture the actual sky above you right now, not a diagram, not a textbook illustration. The real distribution of matter extending outward in every direction from wherever you're sitting. 400 kilometers straight up, the atmosphere ends and space begins. 4 light years to the nearest star system. 100,000 light-years to the far edge of the Milky Way, 2.5 million light-years to Andromeda, 65 million light-years to the Virgo cluster, 520 million light-years to the edge of Laniakea. Then the cosmic web continuing outward for another 45 billion light-years in every direction, with 2 trillion galaxies arranged on filaments separated by voids larger than the structure that contains our galaxy. At the edge of that sphere, a horizon made of time, and beyond it, in every direction, a universe we will never see. You're sitting inside all of that right now. More than 99% of the universe's volume is empty space, not space with a thin scattering of particles, not space with a faint background radiation, though both of those things are real. Space that contains, for all purposes that matter at a human scale, nothing at all. The matter that makes up everything you've ever seen, every planet, every star, every galaxy, every structure across the full observable universe, represents a fraction of the total volume so small that expressing it as a percentage barely communicates the reality. The universe is not a place full of things with gaps between them. It is a place full of absence, with rare concentrations of matter suspended in it at enormous mutual distances. You're made of those concentrations. The atoms in your body are part of the rarest configuration the universe produces, temporary, locally dense, organized in such a way that the organization can contemplate its own rarity and ask what that rarity means. You're not at the center of the universe. You're inside a bubble, and the bubble has a wall, and the wall is made of time. The observable universe contains 2 trillion galaxies. Each holds, on average, hundreds of billions of stars. Many of those stars have planets in stable orbits at distances where liquid water is possible. By raw probability, life should be common. The Milky Way alone, with its hundreds of billions of stars and its enormous population of planets in habitable zone orbits, should contain, if life arises wherever conditions permit, an enormous number of living worlds. The number we can confirm is one planet with observed biology, one civilization capable of building telescopes and asking questions about the universe they inhabit. The most sensitive radio observatories ever built, aimed at the most promising stellar targets for the better part of a century, have returned nothing that any scientific institution has confirmed as artificial. No structured transmission, no engineered signal, no artifact of technology at any scale. The search has been methodical, persistent, and increasingly capable. It has heard nothing it can confirm. Enrico Fermi raised this as a question over lunch in 1950. Where is everybody, given the age of the universe, given the number of stars? Given that a civilization modestly more advanced than ours could, in principle, spread detectable signs of itself across the entire Milky Way in a few million years, well within the age of the galaxy should be full of detectable intelligence. It does not appear to be. One answer connects directly to the void structure Webb has confirmed. Complex communicating intelligence may require a chain of contingencies so specific that it arises far less often than the raw numbers suggest. The emergence of life from chemistry, the emergence of eukaryotic cells, a transition that appears to have happened only once in Earth's history, and may have required an improbable merger between 2 very different types of microorganism. The emergence of multicellularity, of nervous systems, of language, of science, of the institutional structures that sustain technology across generations. If any single step in that chain has a probability of occurring once per trillion planets, then a universe with a trillion planets produces only a handful of civilizations, distributed across volumes of space so vast they might never detect each other, and they might never be able to communicate even if detection were possible. because the causal boundary applies to signals from civilizations exactly as it applies to light from galaxies. Anything beyond the observational horizon cannot reach us. Not now. Not with any future instrument. Not at any speed physics permits. Consider what the void structure means for contact specifically. Even within the observable sphere, civilizations on opposite sides of a void like the Bootes void are separated by 330 million light-years. A signal sent from one to the other at the speed of light takes 330 million years to arrive. A civilization that sent such a signal when the first complex animal life was appearing on Earth would be receiving a reply now, if we'd sent one immediately upon receipt. The structure of the cosmic web imposes communication delays so severe that even civilizations attempting contact across void boundaries would be exchanging messages across spans longer than any civilization on Earth has existed. The universe is not designed for conversation. It is designed for isolation, and now the part that Webb's era has sharpened into something newly uncomfortable. The expansion of space is accelerating, something cosmologists call dark energy, a property of space itself, not of the matter or energy within space, is driving the expansion faster over time. Confirmed in 1998 when two independent research teams found distant supernovae were fainter than expected, meaning farther than models predicted, meaning the expansion had been speeding up rather than slowing. Both teams spent considerable time looking for errors in their data. They found none. The 2011 Nobel Prize in Physics was awarded for the discovery. Dark energy is real, its effect is measured, and its consequence for the observable universe is one of the harder things in cosmology to hold without flinching. The observable universe is shrinking, not in the sense that galaxies are moving closer together inside it, but in the sense of what will eventually be observable from our location. As the expansion accelerates, more galaxies are carried past the causal horizon. Their light, already severely redshifted, is stretched further until it falls below any detector's threshold. And eventually, for galaxies far enough away, the expansion carries them to a distance from which no future light will ever reach us, regardless of how long we wait. In the very long run, tens of billions of years from now, every galaxy outside the local group will have crossed the horizon. The Virgo cluster, currently visible in amateur telescopes under good conditions, will become unreachable. The thousands of galaxy clusters Webb photographs today will have moved beyond the causal boundary. The cosmic web will be invisible from our location, not because it ceased to exist, but because the space between us and it expanded faster than light could bridge it. Any civilization that might exist in the Milky Way at that future time will look out at a sky containing only the local group, perhaps 30 or 40 galaxies in total, surrounded by void extending in every direction without feature. They will have no way of knowing the cosmic web existed, no way of knowing that 2 trillion observable galaxies were once visible from this location, no way of knowing that a telescope called Webb once aimed at a grain of sand's worth of sky and found 10,000 galaxies inside it. The evidence will have moved past the horizon, as completely as if it had never been there. We live in the one era in cosmic history when the universe is most visible to observers at our location. The ancient light is still arriving, the cosmic web is still mappable, the earliest galaxies Webb detects are still within reach. The horizon is at its greatest accessible extent for us right now. In 1 billion years, some fraction of what Webb photographs today will have moved past the horizon. In 10 billion years, more. In 100 billion years, the large-scale structure currently visible from here will be almost entirely inaccessible. The Fermi paradox carries a particular weight when viewed through the lens of the accelerating expansion. Even if civilizations exist throughout the observable universe, the window of time in which they could communicate with each other is finite. As the expansion accelerates, Galaxies in different regions of the cosmic web will be carried past each other's observational horizons, severing not only the physical possibility of travel, but the possibility of any signal exchange. Two civilizations in galaxies that are currently within each other's observable spheres will eventually find themselves in causally disconnected regions as the expansion continues. The universe is not just isolating civilizations from each other by distance. It is actively closing the windows through which contact would be possible. The search for extraterrestrial intelligence, already constrained by the speed of light, is additionally constrained by a universe that is moving toward greater isolation with every passing year. The Webb telescope's contribution to human understanding is not limited to its galaxy counts or its early universe detections. It has also changed the context in which astronomers think about what it means to observe. Webb observes in infrared light that has been travelling for 13 billion years. The instrument that collects that light is a product of human civilization, designed, funded, built, launched, and operated by a species that developed the capacity for astronomy in the last few centuries of a 4.5 billion year planetary history. The ratio between the age of the light Webb detects and the age of the civilization that detects it is roughly 50 million to 1. Webb is a machine of extraordinary sophistication produced by a civilization of extraordinary youth, pointed at a universe of extraordinary age, collecting evidence of events so ancient that the Earth did not exist when they occurred. The juxtaposition is the fact that makes astronomy philosophically significant and scientifically productive simultaneously. What the cosmic web structure tells us about the distribution of everything in the universe can be compressed into a single comparison. The observable universe contains 2 trillion galaxies. Those 2 trillion galaxies occupy roughly 20% of the observable sphere's volume when the full extent of their halos is considered. The remaining 80% of the volume is occupied by voids, regions that contain, for practical purposes, almost nothing. The ratio of void to structure is 4 to 1. For every part of the observable universe that contains a galaxy, there are 4 parts that contain almost none, and within the galaxy containing 20%, matter is further concentrated into stars, and within stars, into the heavier elements that compose planets and life. The fraction of the observable universe's volume that's occupied by anything resembling the matter in your body is so small that expressing it as a decimal would require dozens of zeros before the first significant digit. That fraction is you. That is the proportion of the cosmos that, at this moment, is organized into something capable of receiving and understanding the picture Webb exposed. The universe is not oriented toward that fraction. It does not favor it. It is indifferent to it in the precise sense that the laws of physics operate identically in the densest galaxy cluster and in the deepest void, without reference to whether anything within those regions is capable of observing the operation. You're an accident of matter in a universe of absence, briefly capable of looking outward at the whole and asking what it means. Webb is not simply the most capable telescope humanity has built. It exists at the one moment in cosmic time when the observable universe, from our location, is at its largest accessible extent. The telescope arrived exactly when looking deeply enough still returns the full visible structure. That moment is passing, galaxy by galaxy, carried beyond the horizon by an expansion that has no interest in what it takes. This is not a horror in the conventional sense of that word. It is not a threat approaching. It is something quieter, a confirmed, measured, observed description of the actual universe in which existence occurs. And that description says something specific about the position of any creature capable of receiving it. You are here, in this location, at this moment, made of the rarest matter the universe produces, organized in the rarest way the universe organizes matter. looking out at a structure that is almost entirely inaccessible, that is becoming less accessible every year, that may contain beyond its causal boundary more of everything than any number you have been given could describe, and that will eventually carry all of its visible structure past the horizon until the sky above the Milky Way is as empty as the Bootes void appears today. The universe does not know you are here. It is not oriented toward observation. The 2 trillion galaxies exist whether or not any instrument detects them. The voids have been empty for billions of years whether or not anything alive has ever looked into them. The horizon closes equally on every observable bubble, whether or not anything inside that bubble ever asked what lay beyond it. Consider what the accelerating expansion means for the question of future discovery. Dark energy is not a fixed force, it is a property of space itself, which means as the universe expands and more space is created, more dark energy is created with it. The expansion feeds itself. The more space there is, the faster it expands. This is why cosmologists who confirmed the acceleration in 1998 spent considerable time searching for errors in their data before accepting the conclusion. The implication is that the observable universe is not simply frozen at its current size, it is actively shrinking in terms of what will eventually be accessible to observers at our location. The rate of shrinking is itself increasing. The last galaxy cluster visible beyond the local group will cross the horizon at an accelerating rate. The universe dims faster over time, not slower. The isolation implied by Webb's confirmed scale has a specific character in cosmological discussions, sometimes called the final state of the observable universe. In that final state, a civilization in the Milky Way would have access to the full stellar and planetary resources of the local group but nothing beyond. The local group contains roughly 50 galaxies and a total stellar population of several trillion stars. That is an enormous resource by any human standard. But it is a closed system. No matter, no energy, no information would enter from outside. The civilization would exist in a bubble surrounded by expanding void, with the laws of thermodynamics pushing inexorably toward greater disorder, and with no external input to work against that trend. Before 1998, it was possible to imagine a universe in which gravity would eventually slow the expansion, halt it, and reverse it, pulling all matter back toward a final collapse. In that universe, the long-run fate of the cosmos would be density and heat rather than emptiness and cold. Dark energy eliminated that possibility. The expansion is not slowing, it is speeding up. The long-run fate of the universe, if dark energy continues to dominate as it currently does, is not a crunch, but a slow dispersal and then a silence. Matter spreads. Galaxies recede past each other's horizons. Stars exhaust their fuel. The universe trends toward maximum emptiness and maximum cold on timescales so large that the current age of the universe is a rounding error. There is a version of the current moment worth holding as something other than abstraction. You are alive in the early universe, not early by human standards, early by cosmic standards. The universe is 13.8 billion years old, but the most common type of star, red dwarfs, burn for trillions of years. By the timescale on which most of the universe's stellar activity occurs, 13.8 billion years in is very close to the beginning, and yet the observable universe is already at its maximum legibility. The ancient light is still arriving. Webb can still detect the earliest galaxies. The horizon is as wide as it will ever be for observers at our location. The contradiction between the universe's youth by stellar timescales and its maximum legibility by observational timescales is one of the stranger features of the era we occupy. The personal implication of the void structure becomes clearest when you try to locate yourself within it honestly. You're in the Milky Way. The Milky Way is in the local group. The local group is near the outer edge of Laniakea. Laniakea sits within the cosmic web. The cosmic web occupies 20% of the observable universe's volume, which means that if you were placed at a random location in the observable universe, the probability of finding yourself within a galaxy at all would be roughly 1 in 100,000. The probability of finding yourself on a planet orbiting a star within a galaxy would be far smaller. The probability of finding yourself in a configuration capable of asking these questions would be smaller still by many additional orders of magnitude. You're not in the average location. You're in one of the rarest configurations the universe produces, made of atoms organized into biology, organized into thought, on the surface of a world, orbiting a star, inside a galaxy, on the edge of a supercluster, in the cosmic web, inside an observable sphere, at the one moment when the most ancient light is still arriving. Webb is not simply the most capable telescope humanity has built. It exists at the one moment in cosmic time when the observable universe from our location is at its largest accessible extent. The telescope arrived exactly when looking deeply enough still returns the full visible structure. That moment is passing, galaxy by galaxy, carried beyond the horizon by an expansion that has no interest in what it takes. This is not a horror in the conventional sense of that word. It is not a threat approaching. It is something quieter, a confirmed, measured, observed description of the actual universe in which existence occurs. And that description says something specific about the position of any creature capable of receiving it. You are here, in this location, at this moment, made of the rarest matter the universe produces, organized in the rarest way the universe organizes matter, looking out at a structure that is almost entirely inaccessible, that is becoming less accessible every year, that may contain beyond its causal boundary more of everything than any number you've been given could describe, and that will eventually carry all of its visible structure past the horizon until the sky above the Milky Way is as empty as the Bootes void appears today. There is a thought experiment about Webb's legacy that helps locate the significance of this era precisely. Imagine an astronomer in the Milky Way 1 trillion years from now. The stars are still burning. Red dwarfs live that long. The local group has merged into one enormous elliptical galaxy over the intervening billions of years. The sky contains only that merged galaxy, and the faint glow of dead stars at the Milky Way's location within it. This astronomer looks outward. No cosmic web, no galaxy clusters, no faint smears of light from distant superclusters, no deep field filled with 10,000 ancient galaxies. Nothing, in every direction, but the merged local group hanging in a void that extends without feature to the horizon and beyond. That astronomer, starting from scratch, building a cosmology from what can be observed, would construct a picture of the universe that is radically different from the picture Webb gives us today. They would conclude the universe is small, or at least locally small. They would have no evidence of the cosmic web, no evidence of 2 trillion galaxies. The expansion would be continuing, carrying their merged galaxy farther into its isolation, but with no other galaxies to compare distances against. The evidence for dark energy would be slim. The universe Webb shows us, vast, structured, filled with ancient light, bounded by a causal horizon that is still retreating, is a picture visible only from this narrow window of cosmic time. We happen to be looking out of that window. The scale of the cosmos has been known in rough outline for decades. What Webb has changed is not the outline but the detail, and in some respects the detail is more disorienting than the outline. We knew the universe was large. We knew galaxies existed in enormous numbers. We knew the observable sphere was bounded by a causal horizon. What Webb has added is precision. 2 trillion instead of 200 billion. confirmed intergalactic gas in the filaments, unexpectedly massive early galaxies, quiescent systems that formed too fast. Each detail tightens the description of a universe that was already, in its outline, almost too large and too empty and too permanent in its inaccessibility to absorb comfortably. The details do not make it easier. They make it more specific. A universe that is specifically this large, specifically this empty, specifically changing in this direction, is harder to hold at a comfortable distance than a universe described as large in general terms. The grain of sand that began this is still at arm's length. The sky you look at through it is still the same sky. The 10,000 galaxies in that patch are still there, each one holding hundreds of billions of stars, each one separated from the next by millions of light-years of space that contains, for all practical purposes, nothing. What Webb did was make the accounting more precise. It did not change the sky. It did not move the horizon. It didn't add a single galaxy to the actual universe, or subtract a single void from the actual structure. It looked more carefully at what was already there, with instruments sensitive to wavelengths of light that had been arriving for 13 billion years without anyone to collect them. And what more careful looking revealed is what every previous step of more careful looking has also revealed. The universe is larger, older, emptier, and more permanent in its indifference to any particular location within it than the previous best estimate suggested. Go back to the beginning. Hold a grain of sand at arm's length. Look at the sky through it. You're blocking a patch of sky that, according to the sharpest telescope humanity has ever aimed at the universe, contains roughly 10,000 galaxies, each one with hundreds of billions of stars, each one separated from its nearest neighbours by millions of light-years of space that is, for all meaningful purposes, empty, and each one visible to us only because it happened to emit light in a direction and at a time that allowed that light to cross the full age of the observable cosmos and arrive at this one particular mirror at this one particular moment. That grain of sand is not a small window into a large universe. It is a small window into the fraction of the universe whose light has had time to reach us. Past the edges of what the grain reveals in every direction, the universe continues for a distance no instrument will ever measure and no future civilization will ever see. The actual extent of what exists bears no confirmed relationship to the extent of what is observable. Webb made the observable portion clearer than it has ever been seen. It confirmed 2 trillion galaxies where textbooks had printed 100 billion. It detected the intergalactic gas of the filaments. It found galaxies that should not exist as early as they do. It gave us the most detailed and accurate picture of the accessible universe that any instrument has ever produced. And the most detailed and accurate picture of the accessible universe is a picture of a structure that is, by every measure that matters, mostly inaccessible. 2 trillion galaxies. A structure dominated by voids larger than the supercluster that contains the Milky Way. A horizon made of time rather than distance, drawing a boundary that no signal has ever crossed and no signal ever will. An expansion carrying more of the universe past that boundary with every passing year. And a direction of change, the accelerating expansion, that ensures the picture we have right now is the most complete view any observer at our location will ever have. We are at peak visibility. The universe is dimming from here. Webb also gave us something harder to quantify than a galaxy count. It gave us confirmed proportion. Before Webb, the 2 trillion figure was a model output. After Webb's first deep fields, it was direct observational conclusion. The photographs are not illustrations of the scale. They are the scale itself, rendered in ancient light, arriving after 13 billion years of transit across an expanding universe, collected by a mirror built by human beings at the one moment when the collecting was still possible. The 2 trillion galaxies visible from our location are not uniformly distributed in time. Nearby galaxies appear to us as they were millions of years ago. Mid-distance galaxies appear as they were billions of years ago. The most ancient galaxies Webb detects appear as they were 13 billion years ago. The observable universe is not a snapshot of the universe at one moment in time. It is a composite of different eras, each galaxy shown at the moment corresponding to its distance from Earth. Looking at a Webb deep field is like looking at a history book whose pages show different centuries simultaneously, with the most ancient pages at the edges of the field and the most recent pages near the centre. We are surrounded by the past in every direction. The present state of any significant structure at any significant distance is hidden from us behind the finite speed of light. The silence of the sky at night, the fact that the sky is dark rather than uniformly bright with starlight, is itself a consequence of the universe's finite age and the causal horizon. If the universe were infinite in age and extent, with stars in every direction at every distance, the sky would blaze with uniform light. Every line of sight would eventually terminate on a star or galaxy, and their combined light would overwhelm the darkness. The sky is dark at night because the universe is young enough that light from most of it has not had time to reach us, and because the expansion of space stretches and dims the light that does arrive. The darkness above you right now is not emptiness. It is the silence of the causal horizon, the universe speaking through its absence. What Webb exposed with its deep fields is not the universe itself, but the universe's message to our location, filtered through 13.8 billion years of transit. It is the sum total of all the light that happened to leave the right sources at the right times in the right directions to reach a mirror in space at the right moment. Every other photon, from sources at other distances, at other times, in other directions, or from beyond the causal horizon, was not in that message. The message is enormous. It contains 2 trillion galaxy records and ancient cosmological data, and the chemical signatures of stars that burned and died billions of years before the Earth formed. But it is a small fraction of the universe's total transmission. Most of the universe will never send us a message at all. Somewhere beyond the horizon, in the volume no signal has ever crossed, something may exist that is as complex and as searching as anything here. Looking outward from its own location, bounded by its own horizon, holding its own grain of sand up to its own dark sky, finding its own 10,000 galaxies, asking its own version of this question. We will never know. The grain of sand remains. The observable universe is 93 billion light-years across. It contains 2 trillion galaxies. It is bounded by a causal horizon that no instrument will ever cross. It is embedded in an actual universe whose size is unknown and almost certainly vast beyond any number we have given it. It is changing right now in a direction that makes it less visible and less accessible with every passing year. And within it, at one location in one galaxy on the outer edge of one supercluster in a web dominated by the emptiness between its threads, a species that has existed for a few 100,000 years built a machine and pointed it at a patch of sky the size of a grain of sand held at arm's length, and found 10,000 galaxies inside, and from that one data point calculated the rest. That calculation is what Webb confirmed. The grain of sand is what it started with. The grain of sand is what it ends with. The light that formed Webb's first deep field image is no longer travelling. It arrived. It completed a 13 billion year crossing of an expanding universe and landed on a mirror. The galaxy that sent it still exists, transformed beyond recognition by 13 billion additional years of evolution, receding from us at a speed proportional to its distance, carrying its current light toward a horizon that our location can never receive. The ancient light is gone from the universe. absorbed by Webb's detectors, converted into data, transmitted to Earth, processed, and turned into an image. But the universe kept expanding while that happened. More galaxies have crossed the horizon since July 12, 2022. More will cross it tonight. The grain of sand looks at the same sky it always looked at. The 10,000 galaxies are still in that patch. Some of them, in the time it takes to read this, have moved fractionally farther from us. The count is the same, the accessibility is fractionally less. That is the universe as it actually operates. That is the picture Webb exposed. Webb's first deep field was revealed on July 12, 2022. In the time since that image was released, the universe has continued its expansion. The galaxies at the edge of the observable sphere have moved fractionally farther away, their light fractionally more redshifted. Some number of them, too small to measure over a human lifetime, have crossed the causal horizon and become permanently inaccessible. The count of 2 trillion is fractionally smaller than it was. The accessible portion of the universe is fractionally less than it was on the night those images were first shown to the public. The rate of change is too slow to observe on any human timescale. But it is real, and it is irreversible, and it has been happening since the first moment of the universe's existence, and will continue until the last galaxy cluster outside the local group vanishes beyond the horizon. We are in the middle of that process. We always have been. Webb has made the middle visible.